All right, so problems from chapter 14. Yeah. This this says, suppose you have a coffee mug with a circular cross section and vertical sides. What is its inside radius if it holds 375 grams of coffee when filled to a depth of 7.5 centimeters? Yeah. So here everything is in centimeters, and we'll keep those units. Yeah. So So the density of coffee is the same as the density of water. That's what we'll assume. And the density of water is 1 gram per centimeter cube. Okay. So in these units, and so density, of course, is mass divided by volume. So volume is mass divided by density, which is 375 grams divided by 1 gram per centimeter cube. So the volume of coffee is 375 centimeter cube. And what we want to find is the inside radius of the cup. So here's the cup. Okay. And we'll assume the coffee is filled to that height. Okay. So volume is area of cross section times the height. Okay. So the radius of the cup is volume pi h square root of that. Yep. The volume is 375 centimeter cube. The coffee was filled to 7.5 centimeters. Okay. Okay, so this will work out too. About 4 centimeters. Okay. So roughly 2 inches for the radius. Okay. Okay, this problem says a trash compactor can compress its contents to 0.35 times its original volume. So neglecting the mass of air expelled, by what factor is the density of rubbish increased? Okay, so a lot of trash is compacted. So why do we do that? Because it occupies less volume and there's less volume dumped into a landfill. So density is mass divided by volume. Okay, so final density is the mass is the same and it's the final volume. So this is mass divided by 0.35 times the initial volume. So you decrease the volume to 35% the initial volume. So this is equal to 1 over 0.35 divided times the initial volume. So roughly 3 times the initial volume. I mean, 3 times the initial density. All right, in this problem, a dam is used to hold back a river. So there's the river. It has a height of 12 meters. 12 meters is roughly twice the height of this room. Okay. And a width of 10 meters. 10 meters is roughly half the width of this room. Yep. So it's a small dam. Assume that the density of water is that. Determine the net force on the dam. Okay. So you know that the pressure increases with depth. Okay. So the pressure at any depth is P naught. P naught is the atmospheric pressure at the top. Okay. And plus rho g h, where h is at that depth. Okay. Now the net force is, what is the pressure here? The pressure here is atmospheric pressure as well. Okay. So the net force in this direction is the force due to this pressure minus the force due to that pressure. So the force is just rho gh times the area, okay, and the area of this strip. Okay, so it's gauge pressure times the area of that strip. Question? Okay. Does it make sense?
Yeah.
Okay.
Sounds like we need to do an integral.
I'm sorry?
Sounds like we need to do an integral.
Yeah, we will. Yeah, so we're just setting up the integral. Okay. All right, so this area, what is this area? The area is the width times this height. Okay. So the force on this strip, this force is the gauge pressure times the area of the strip. So we'll call it dF. dF is gauge pressure times width times the dy. Okay. Now, so the total force is the sum of all those forces. The force on this strip plus the force on this strip plus that. Okay, so that's what this integral is. Okay. It's the sum of those forces. Okay. So rho gh w dy. So we're doing an integral over y. All right, so let's write everything in terms of y. Okay, what does y change from? Y is in this direction. It changes from 0 to h. Rho g h. Little h, we want to write that in terms of y. Okay, can somebody tell me what that is in terms of y? I'm sorry? So it's h minus y. Okay. Okay. So, so that was the most involved part. And now that we have written it as an integral, yep. Yeah. Okay. Now this integral is easy to do. Okay, so this is rho g w, that's a constant, and hy minus y squared by 2. And the limits of integration are 0 to h. Okay. All right, so, oops. So that's the force, and the force is rho g w h square. When we apply the limits to y, it's h minus 0, so h square minus h square by 2. All right, so that is the expression. Now let's write it in terms of, let's write it so that this makes a little more sense to us right now. So this is rho g, width times h is the area of the wall, times h by 2. So area of the wall. See, force is pressure times area. And what is this? This is the gauge pressure on the wall. It's the average gauge pressure on the wall. See, the pressure, the gauge pressure increases with depth, and this is the average pressure times the area of the wall. Okay, so that's the force on the wall. Yeah. And that makes sense, okay. Now in part B, they ask you, why does the thickness of the dam increases with depth? See, the force on this strip increases with depth. And so you're pushing harder, so the wall has to be thicker, okay. The friction between this layer and that layer holds it back. Yeah. Again, this is the average gauge pressure times the area of the wall. Okay, this problem says, assuming bicycle tires are perfectly flexible and support the weight of a bicycle and rider by pressure alone, calculate the total area of the tires in contact with the ground if a bicycle and the rider have a total mass of 80 kgs. So, and a gauge pressure in the tire is, what is this? 10 to the 5 pascals, what is that? 1 atmosphere, very good. So it's, the gauge pressure is 3.5 atmosphere. So the actual pressure is 4.5 atmospheres, okay? Yep.
Question, when I was doing this formula review, the formula that you use, do you know if they say gauge pressure specifically, you should try and find the absolute pressure if you're using a formula then?
Which one? In the
In
previous?
this question, yeah.
No, we'll be using the gauge pressure, you'll see in a second.
Okay.
Just like in this problem, see, the net pressure here was P naught plus rho GH, but there was a P naught over here as well, and that canceled that, so you used only the gauge pressure. Same thing will happen in the tires as well. So notice, this is the gauge pressure is 3.5 atmospheres. What is the pressure in your car tires? 30 psi, which is two atmospheres, the gauge pressure. So the pressure in your cycle tires is greater. Why is that? Your car is so much heavier. Well, and also each wheel has a lot of area in contact. Okay. Yeah. So, and you'll see that in those racing bicycles, the area is even smaller than in my mountain bikes, and the pressure is higher. Yeah. All right. So, what we'll do is we'll draw just one wheel. We'll say this is a unicycle, and this much area is in contact with this road. All right, so gravity is pulling this down, okay, and this object along with the passenger is in contact with the ground, and so the ground is exerting a force normal force on that piece of rubber. That piece of rubber is not moving. Okay, so the normal force should equal mg. Okay. Now, so this is the normal force. This is on the piece of rubber. There's the air pushing it down. Okay. So the reason this rubber is not moving is because this air is exerting a force. Okay. So the force exerted by the air in the tires. Okay. Okay. Well, so I didn't quite draw everything there. So the air inside is pushing on this piece of rubber, and the air outside is also pushing on this rubber. Okay. Even though this sheet of paper is sitting on the table, the air underneath is enough to push it up. Okay, just like that. The air underneath the tire is pushing it up. Okay. So what you want is the net force is just the gauge pressure. Okay. So the gauge pressure of the area times the area of contact times the area of contact is equal to Fn equal to the weight. So this is the area of the tire in contact. Okay, so the area is the weight of the passenger and the bike divided by the gauge pressure in the tires. Okay, so you see this equation, the more weight you have to support, the higher the gauge pressure of the air has to be in the tires. Okay. And if you want a small area, the gauge pressure has to be higher. So in racing bikes, the area of contact is smaller, so the pressure of air in the tires is higher for the same weight. Okay.
Right, will we divide that by two tires, or would that keep the same?
So this is the total area in contact. Okay. I didn't want to draw 2 tires and all that stuff. Yeah. I have a hard enough time drawing 1 tire. All right, so everybody understand that? So this is the gauge pressure. Again, so this also explains the following to you guys. So greater the mass for a given gauge pressure, greater the area. Okay, so what do you do in semi trucks where you have to support a lot of weight? What's that? Have more tires. That's what you do. Okay. You don't want to increase the pressure too much. You don't want tires exploding. So when you're lifting heavy loads, what you do is you keep adding tires. Okay. And if you don't want axles to break, you keep adding axles. And if you reach the limit, then what do? You buy more trucks. Okay. All right. So. All right. So now we can put in the numbers. This is 80 kgs is what we are supporting. And the gauge pressure is 3.5 into 10 to the power 5 pascals. Okay, so everything is in SI units, and so the area will come out in meter squares. Yep. Okay, what I'll do is So this is 8. I'll take that 10, make that 10 to the 4. That comes to the top, becomes 10 to the minus 4 meters square. Meter square. And 10 to the minus 2 meters is 1 centimeters. Okay, so this is centimeter square. So the area is 22.4 centimeters square. Okay, and so if you take the square root of 22.4, that's 4.73 centimeters square. So the area of contact is 2 inches by 2 inches, about that much, total area of contact. Okay?
Explain again why we're using the gauge pressure in the tires and not the absolute pressure.
Okay, so this is the tire that we're looking at, that piece of rubber that we're looking at.
Yeah.
The inside air is actual pressure times the area, that's what it's pushing. But the outside air is also P naught times area. So the force of the air is P minus P naught times the area. And this is gauge pressure. Okay. So if you had perfect vacuum here, then you would use absolute pressure. So if you were riding the bike on the moon, then you would use absolute pressure. So this problem says, what force must be exerted on the master cylinder of a hydraulic lift to support a weight of a 2,000 kg car resting on a secondary cylinder? The master cylinder has a diameter of 2 centimeters, and the secondary cylinder has a diameter of 24 centimeters. Okay, so this is so here is the master cylinder. When you push on this, you get the output force on the slave cylinder. Okay, and this diameter is 24 centimeters, almost a foot, and this diameter is 2 centimeters. Okay, so essentially this is a machine. It's a force multiplier, and the output force, it's very simple. This is the input force, this is the output force, and you saw from your notes the output force is the output area divided by the input area times the input force. Okay, so this is Pascal's principle. This is the increase in pressure. This is the increase in pressure here. And Mr. Pascal tells you, if you increase the pressure at any location in the fluid, that increase in pressure is transmitted everywhere. And so output force divided by output area, that's the output pressure. So if you increase the pressure at this location, that same increase in pressure is seen there. Okay. So here's the output force. Okay. Here's the output area. Okay, so it's a simple calculation. The diameter is 12 times the input diameter. Area is proportional to the diameter square. So the output force will be 144 times the input force. Okay? So here's a force multiplier. It multiplies your input force by a factor of 144. Okay? All right, so the output force is pi diameter squared by 4. The area of a circle is pi r squared, which is, okay. So the output force is 144 times the input force. Okay. Well, you're given the output force. You're lifting a 2,000 kg car. So that's the output, 144 input G. So that is the weight you're applying in the input side. So the input mass is 14 kgs. 14 kgs is roughly 35 pounds. Okay. So you apply 35 pound force and you're lifting a 4,500 pound car. 2,000 kgs is 4,500 pounds. Okay. So you can just push that with your hands and lift the car up. Yep.
The force out, how did you get the pi diameter squared divided by 4?
The area of a circle is pi r square. The radius is diameter by yeah. Any other questions on that? All right, so again, what is this? It's a machine, it's a force multiplier. This is an input force, and you're getting a large output force. Okay, so you can do the same thing with, as long as the area increases, you get a large output force. So this is a similar problem. So you can do this at home. So you have a hydraulic press at home. So okay, so here's a wine bottle. Okay, so a host pours the remnants of several bottles of wine into a jug after a party. The host then inserts a cork with a 2 centimeter diameter into the bottle, placing it in direct contact with the wine. So it has to be Okay, so the cork has to be, so it's filled with wine. And again, you apply a force here. It's a small area. This is a large area. What you get is the output force here. So the input force and the output force. You increase the pressure at this point by F in times area in, and you get the same pressure increase at that point. Okay? So F in divided by area in. Just like in the hydraulic press. Okay, this is Pascal's principle. What Mr. Pascal said, in an enclosed fluid, if you increase the pressure at any location by a certain amount, that pressure is at every point in the fluid, the pressure increases by the same amount. Okay, so likewise at this point, the pressure increases by the same amount. Yeah. Okay. So the host is amazed when the host pounds the cork into place at the place, and the bottom of the jug with 14 centimeter diameter breaks away. Okay, so you pound this force. Calculate the extra force exerted against the bottom if he pounds the cork with a 120 Newton force. Okay, if the input force is 120 Newton, what is the output force? Okay, so you can do this with a fluid at home, and but the glass bottle will break, so you got to be careful. Okay, so 14/7 square. So 14 divided by 2 is 7. 7 square is 49. So you're getting a 50 time multiplication of the force by a factor of 50. Okay. So the input force is 120 newtons, and the output force will be 6,000 newtons. That'll be enough to separate the bottom of the glass from its joint. Did you guys understand that? See, all these force multipliers, the input force is applied over a small area, and you get a large output force. Okay, in this problem, a person's body has a density of 995 kg per meter cube. What fraction of the body will be submerged when floating gently in fresh water? The density of fresh water is 1,000 kg per meter cube. Okay, so when an object is floating in a body, so the density of the object divided by the density of the fluid, so in this case it's water, is equal to the volume displaced divided by the volume of the object. Okay, so when the density of the object is less than the density of the fluid, this number is less than 1, and then this can have a solution which is less than 1. Okay, so the displaced volume will be less than the volume of the object. So here's the fluid. Okay, so the object can float only when its density is less than the density of the fluid it's floating in. Okay, So this volume is that volume, that's the displaced volume. And this is the volume of the object, which is that. Okay, so whenever an object is floating, that means this is less than 1, and so this has to be less than 1. Okay. All right. So they ask you what fraction of the body is submerged in this thing. So displaced volume divided by the volume of the object, that's the fraction that's submerged, is 995 kgs divided by 1,000. So 99.5% of the volume of the body is submerged. Okay. So in principle, if you don't panic, you can just stick your nose out and stay afloat. What you can also do is, it turns out that you can take a deep breath, fill your lungs with air, and your density decreases, and your nose will stick out further. In salt water with a density of 1,027 kilograms per meter cube. There, you have more room for error. You can probably stick your whole nose out. And I'm sure you've seen pictures of the Dead Sea, people. Okay. So, people floating in the Dead Sea, it's very salty. You see that the density in Dead Sea is quite large. Okay. So in the Dead Sea, you're almost only 80% of your body is underwater. All right, so this problem says calculate the buoyant force on a 2-liter helium balloon. So this is a small balloon that you can buy at Publix or whatever. Given the mass of the rubber in the balloon is 1.5 grams. What is the net vertical force on the balloon if it's let go? Neglect the volume of the rubber. Okay. That's funny. There's no A. That should be A, I guess. So here's the balloon. Okay, here's the weight of the balloon. What does the weight include? The weight includes the weight of the rubber plus the weight of the helium. What is the buoyant force equal to? Mr. Archimedes tells you what the buoyant force is equal to.
The rate of the air that was displaced.
Right, it's the weight of this much air that was displaced. Okay, and the reason this thing floats is because this fluid has to be less dense than the surrounding fluid, which is air, whatever is displaced. Okay, that's when you float. Okay, so the buoyant force is equal to this weight, and the buoyant force is the density of air. It's the weight of the displaced fluid times the volume of the balloon times g. Okay, and what is this mass? This weight is mass of helium plus mass of the rubber times g. Okay, the g's cancel. So density of air times the volume of the balloon is equal to mass of helium. Mass of the helium is density of helium times the volume of the balloon plus mass of the rubber balloon. Mass of the rubber. Okay. So what is it that we're finding? What are we looking for? It's a 2 liter. What is the net vertical force? Oh, we are finding. Oh, okay. So the net vertical force is the buoyant force minus mg. Oh, so this is not true. So the buoyant force is weight of air displaced. Okay, I'm sorry, that was not right what I did before. Weight of air displaced equal to rho air okay, that's the buoyant force, and mg is rho helium volume times g plus mass of rubber times g. So now the net force in the upward direction is this buoyant force minus mg. Okay. Okay, the buoyant force is density of air times volume times g minus density of helium times volume times g plus mass of rubber times g. Okay, that's the net upward force. Okay, what we'll do is we'll calculate this. Okay, I'll do it in funny units. Okay, this is G, this is the mass of the rubber, which is 1.5 grams. So what we'll do is we'll calculate this in grams, and we'll see the upward force as in relation to the rubber weight of the rubber balloon. Yeah? So we have to look up the density of air and helium. Density of air is 1.3 kgs per meter cube, and 1.3 kg. A meter cube is 10 to the power of 3 liters, and kg is 10 to the power of 3 grams. So it's 1.3 grams per liter. Okay, roughly this is a liter, this bottle. So the density of air is about 1.3 grams per liter. What is the density of helium?
Zero point 1786 grams per liter.
0.
1786.
Okay. All right, so the density of helium, air minus the density of helium, so what we're doing is we're calculating this, yeah, times the volume. We'll call it 1.8 grams per liter times 2 liters. So this is 2.24 grams. And you see, this term is 2.24 grams. What is the mass of the rubber balloon? 1.5 grams. So there's a net upward force. And so this balloon will rise. Okay. Okay. So I hope you guys are understanding this. So let's calculate, when will the balloon not rise? When will the balloon not rise?
Air density is equal to the density of the helium.
No. So when this term is equal to this term. Okay, so when this thing is 1.5 grams. Okay. So, and you can work this out. So this times the volume should be 1.5 grams. So 1.5 grams divided by this will give you the volume. And I'll tell you that in a second. And the reason I'm doing that is so the minimum volume of the balloon needs to be 1.34 liters. Okay? So you need to fill more helium than that for it to rise. Okay? Did you guys understand that? Okay. So there's a great story. So this balloon, and just for the heck of it, we'll calculate the acceleration of this balloon. Okay. So let's calculate the acceleration of this balloon. Acceleration is the net force upward divided by the mass. Okay, that's rising. The mass is the mass of the rubber and the mass of the helium. Okay. And the net force is there's this guy's 2.24 grams. So the net force is this guy minus the mass of the rubber times G. Okay, you guys can review this after you go home. Minus 1.5 grams times G divided by, now I have to get the mass of the rubber plus mass of the helium. Yeah. 2.24 minus 1.5 grams times G. Okay, this is a little confusing, but grams times G divided by 1.5 grams plus mass of helium was, what was the density? It was 0.18 grams per, mass of helium was 0.8 grams per liter times 2 liters, 0.36 grams. Times G. Okay, so this was the acceleration of the balloon upwards. You guys can review the math when you get home, but I'll tell you a story. So this is 0.74 divided by 1.86. 0.4 G. So the acceleration of this balloon is 0.4 G. Okay, 4 meters per second squared. Okay. What will happen to the acceleration if the balloon weight is the same and you increase the volume? If you increase the volume, the acceleration will be greater. Okay. So several years ago, apparently this is a true story. Maybe some of you have heard about it. So this retired postal service guy, he got onto a lawn chair behind his house and attached several helium balloons to his chair. And he rose up. And he had a little BB gun as well when he wanted to come down. And he got into the Los Angeles air traffic. I mean, pilots coming into land had a sight that they had never seen before. So, and he survived to tell the story. So you can, let's. I don't know if well, anyway, you can Google that. Okay. Okay. This says, estimate the time it would take to fill a private swimming pool with the capacity of 80,000 liters using a garden hose delivering 60 liters per minute. How long would it take if you could divert a moderate-sized river flowing at 5,000 meters cubed per second into the pool? Okay, so volume is flow rate times time. Okay, flow rate is volume per unit time times time gives you the total volume that you're filling. Okay. So time would be, flow rate would be the total volume that you're filling divided by flow rate. Okay. So in the first case, so you're filling this 80,000 liter pool, and the flow rate is 60 liters per minute. So it takes you 8,000 divided by 6. So if you're filling a pool with a garden hose, it takes you that many minutes, 22 hours. Okay? So it'll take you all day to fill the pool with a garden hose. But if, on the other hand, if you divert a river to fill it, okay, 1,000 liters is a meter cube. So this is 80 meters cube. So if you use a flowing river to fill it, this particular flowing river to fill it, so it'll take you 0.016 seconds, 16 milliseconds to fill it. Okay. The only problem is you don't know how to shut off the river. Okay. All right, this problem says every few years winds in Boulder, Colorado attain sustained speeds of about 100 miles per hour. Okay. When the jet stream descends during early springs. Okay. So you guys know jet streams are so you see jet streams are flowing rivers. They're about these guys flow about 11 kilometers up in air, and if you're flying east, then planes will get in these jet streams. These jet streams could be going at 100 to 200 miles an hour. Planes fly at 600 miles an hour. So you get in there, it's you save fuel. Okay? If they're going in the same direction, and these guys can be about as wide as from here to Beach Street, okay? And so on. See, there's the jet stream. Okay. All right, so here's the deal. So here in Colorado, here's a mass of air that's flowing fast, okay? And if you look at Bernoulli's equation, this is pressure plus, okay, and here is the potential energy term is constant. Okay, so the Y for this air that's blowing above your roof and inside, this is not changing much. So when the air speed increases, when the fluid speed increases, the pressure decreases, since the sum of these two terms is constant. So when a fluid flows faster, the pressure decreases. Okay. So this air is flowing fast. The pressure here is low. What is the pressure inside your house? Inside the house there? 1 atmosphere. Okay, the pressure here is low, the pressure here is high. There's a net force in the upward direction, and that can blow your roof off. Okay, so that's what happens in a hurricane. All your windows and roofs get blown in from the inside. Okay. All right, we'll calculate that. And that's what happens in a plane. In a plane, the airfoil is shaped such that it makes the air go faster at the top than at the bottom. The pressure here is low, the pressure here is higher, and so the force of the lift is high pressure minus low pressure times the area of the wing. Okay. This depends on the speed of the plane, which is the speed at which the plane is. So this difference in air speed will depend on how fast you're flying. Okay. So if you're flying a big heavy plane, what do you have to do? Well, this is only so much you can do about this. You have to have large area wings. Okay. All right. Anyway, so coming back to this problem, so every few years, winds in Boulder attain sustained speeds of about 100 miles an hour when the jet stream descends during early spring. Approximately, what is the force due to Bernoulli's equation on a roof having an area of 220 meters square? 220 meters square would be about half the size of this room. Okay. Typical air density in Boulder is this, and the corresponding atmospheric pressure is 8.89 times 10 to the 4 Newton per meter square. So 0.899 atmospheric pressure in Daytona Beach. Okay, so in Boulder, the pressure inside the room is 0.889% the pressure here. Okay. Okay, so now let's calculate this. So we'll say this is location 1, location 2. Okay. So pressure at location 1 plus 1/2 rho V1 squared at location 1 plus rho G Y1 equal to pressure at location 2 plus 1/2 rho V2 squared plus rho G Y2. Yeah. Rho is the density of air, and this guy Y1 and Y2 are roughly the same, so we'll cancel this. Okay. Anyway, that contribution will be very small. If you take the difference would be about 6 inches. Okay. So the air inside is at rest, that's still, so this guy is 0. Yep. So P2 minus P1 is equal to 1/2 rho V1 squared. And so P2 minus P1, and the net upward force is P2 minus P1 times the area of the roof. So that's equal to 1/2 rho V1 squared times area of the roof. Yep. So half the size of this room, and if the jet stream is blowing by your roof, this will be the force, upward force on this roof. That's what we're calculating. And in Florida, you get 100-mile-an-hour winds easy. So, yeah. So you can calculate the net upward force. Yeah. All right, so the net upward force is 1 rho V1 squared times the area. Right, the density of air in Boulder is 1.14 kg per meter cube. The velocity of air is 45 meters per second. And the area is 253,000 newtons. So this is roughly, if you divide by G, which is 10, this will give you 25,400 kgs, roughly. Okay, and that's the weight of 10 cars. So the question is, can your roof support the weight of 10 cars if we park 10 cars on your roof? Yeah. Except that this force is pushing upward. And so that's why when those insurance adjusters come and inspect your homes, what they're making sure is those hooks holding your roof up or your roof down are good enough.